Good morning. Today we'll discuss more problems on Norton's theorem. In the last lecture, we have seen a simple problem on Norton's theorem. Now we will move on to a little bit more complex problem on Norton's theorem. I hope that you will be able to determine Norton's equivalent of given circuit. So, a quick review. Any complicated network can be replaced by a Norton's equivalent, which consists of a current source, which we call it as a Norton's current, in parallel with a resistance, which we call it as Norton's resistance. So the quick review of the steps. The first step is removing the elements. The second step, short circuiting the terminals and determining IN. Third step, replacing all the independent sources. Number 4, determining RTH by open circuiting the terminals. Do remember, while doing RTH, you are supposed to open circuit the terminals. And number 5, it is drawing the Norton's equivalents. So with these 5 steps, now let us try to determine the Norton's equivalent of a given circuit. See, find the Norton current for the unbalanced Wheatstone switch shown in the figure below. This type of circuit is normally called as a Wheatstone switch. See, this is excited by a 10 volts voltage source, and there are 4 resistances here: 10 ohms, 30 ohms, 20 ohms and 40 ohms. And this is here AB terminals, which I call it as load resistance. Now you are supposed to remove this one and do your problem. So I will follow the 5 steps. Step number 1 is removing this resistance. So if I remove this resistance, you will get A and B terminals. Now for doing step number 2, you need to short circuit these terminals, right, to determine the Norton's current. So I am short circuiting these terminals. This is step number 2. Short circuiting comes in step number 2. So I will short circuit these terminals and I will determine the current through it. Okay. See. Now, since this is being short circuited, I'll take this one as IN. Okay. Now, if you carefully see, now I can apply nodal analysis. First, let us determine the effective nodes. This is 0. So defaultly, this will become 10 volts. Right. So this I don't know. I'll take it as V1. And here, this is already 10 and there is one more node. But if you carefully see, this is completely short circuited. So whatever V is here, the same will be present here. So instead of V1, I'll take just only as V. Okay. V. So there is only one effective node. This completely is one effective node. This is completely one node and it has 4 paths. This is one path, second path, this is third path, and this is fourth path, right? So when I start applying KCL at this effective node, see what are the paths. Path 1, V minus 10 by 10 plus V minus 0 by 20 plus V minus 10 by 30 plus V minus 0 by 40. So this is your combined equation at this particular short circuited node. If I solve this one, I'll get the value of V is equal to 160 by 25, that is equal to 6.4 volts. Okay, so this particular point is at 6.4 volts. Right, so now this is short circuited. Now this point is at 6.4 volts. This is also at 6.4, this is at 0 and this is at 10 volts. Now you can go with your, now you need to determine the current in this path, right? You can apply KCL at any of the path again. I'll choose this particular point. How many paths it has? 1, 2 and 3, right? So by KCL at this particular point, you know that sigma I is equal to 0. How many paths it has? 3 paths. I'll take this one as I1, I'll take this one as I2, I'll take this one as I3. which is nothing but IN. So I1 plus I2 plus I3, which is equal to 0. What is I1? 6.4 minus 10 by 10. Plus what is I2? 6.4 minus 0 by 20. And what is I3? I3 is nothing but my desired current, which is IN. To solve this, you will get IN as 0.04 amperes. Understood now how to obtain the Norton's current, short circuit current. First I have tried nodal analysis and then I tried this case here. Now, so the problem ends here because they are asking us only to determine the Norton's current. But if you want to determine the Norton's resistance or the Thevenin's resistance also, in step number 3, what I must do, I must replace this resistance and I must open circuit this one. See here, I have open circuited this one. And the sources are to be replaced. See, there is one source here and it is to be short circuited, right? So the voltage is to be short circuited and this is the network. See here, the voltage has been short circuited. The remaining resistances are kept in their positions. This is A and B. Now what I am doing is, for easy understanding, let us redraw this figure. Okay, when I am trying to redraw this figure, if you carefully see, I can keep this A and B, I am shifting this A and B to sideways and I am bringing this point which is joining these two terminals. If you carefully see, there is a short circuit between these two terminals, right? I can write it, I can draw it in between also directly, right? The same I am doing. See, I am just taking these AV terminals outside and I am shorting these terminals which was earlier outside. That I am trying to see this line whichever is present here, I am drawing it inside. So this is, I am drawing it inside. Now if you carefully see, as already I told you in the class, the best way is nothing but these two resistances. If you carefully see, these are in parallel. See, it is connected between this point and this point, and this is also connected between this point and this point. So I can see that these two resistances are in parallel. So that's why I have mentioned it as 10 and 20 as in parallel, and 30 and 40 are also in parallel, isn't it? 30 and 40. Now you can easily calculate the net resistance. What is the net resistance? 10 and 20, both are in parallel, right? So its value is going to be 10 and 20. Its value is going to be 6.66. And for 30 and 40, the value is going to be R1 R2 by R1 plus R2. This is the equivalent resistance for two resistances which are connected in parallel. So for 30 and 40, I will get 17.14. Now both this combination is available in series. So if I add these two, I will be getting my RTH. Okay. So the equivalent resistance is 23.8 ohms. Now the step 5 is about, I have already got IN is equal to 0.04 amperes and RN is equal to 23.8 ohms. So I am connecting them both in parallel. This is IN with RN. And the resultant, if you want to determine the voltage drop across this one, you can keep it in parallel. The resistance which we have removed at the start, this is R. If you want to keep here, you can keep here. Now this is here Norton circuit. And this is here load resistance. If you want to do some more calculations on load resistance, what is the current flowing through the load resistance? What is the voltage drop across it? Then you need to do some more calculations. So let us see what is the current which is flowing in this one. I. See, there is a current. This is one path and this is another path, which means both are in parallel. I can use current divider rule, right? So total current is 0.04 into, I need current in this one. So I am taking 23.8 by 23.8 plus 50. Because I1 is to I2 is equal to 1 by R1 is to 1 by R2. So if I calculate it, I will get, this is the current which is flowing in this 12 milliamperes. Okay. Now, if I want to calculate the voltage across AB, so what is the current flowing? 12 milliamperes into 50 ohms. This will be the voltage drop. I will get around 6.6 volts. Okay. So like this, you will be calculating the Norton's equivalent. circuit, or the Norton's current, or the Thevenin's resistance, or any voltage drop, or the current flowing through the load terminals. I hope that now you are able to determine the Norton's equivalent and also determine the load parameters. So this is your homework problem. Try to determine the Norton's equivalent circuit for the figure, and also determine the current which is flowing in the 8 ohms resistor. Okay. So we will discuss more problems in the class. Come prepared for the class. Thank you.